Welcome back to ECE 501B. Homework 6 is due today. Is that correct? And our exam is Wednesday. The exam is over material in homeworks 4, 5, and 6. And I'm thinking since we didn't have yet an opportunity on a homework set to look at Graham-Schmidt, we won't go quite that far on exam 2. So there's not a whole lot to test on in exam 2. It's chapters 5 and 6A, the first piece of chapter 6, up to the sections that we basically had homework material on, which is inner products. What else did we have? Cauchy-Schwarz, parallelogram equality. I'm missing one. Pythagorean theorem, those kinds of notions relative to the inner product. So become an expert on the inner product. And the homeworks for 4, 5, and 6, and that's what I will try to create an exam that spans. You actually could go back, I think, to exam 1, the old exam 1. There is an eigenvalue, eigenvector problem on that. And some of the material in the practice exam number 2, you won't be necessarily held responsible for. The optimization stuff, meaning when are you orthogonal and orthogonal projection. It's mainly now just inner products and up through the material that's covered on homework number 6, which is due today. Is that clear? And we'll talk more about the process of exam 2 at the beginning of today's class. The process. I've tried to sort of give you an overview of what to expect. There is practice material, I believe, on D2L, but don't forget to go back and look at exam number 1 practice material because we didn't get as far this fall as last fall. So there is material on the old exam 1 that is pertinent to this exam for you guys in exam number 2. Then once we finish up talking about the exam 2 process, we will continue with chapter 7. We'll talk about the adjoint operator just to get us thinking again about chapter 7. That's the wrong way to start a lecture, isn't it? Let's move into new material, which won't be on the exam, but it will be on the final. So don't check out on me today, please. Okay? I can check out, but you can't. Okay? We'll recap the adjoint and what it means to be self-adjoint in terms of an operator. Then we will examine the behavior of a simple linear map, and about as simple as you can get is a 1 dimension to a 1 dimension, a scalar mapping. That's a matrix, but if you put it into a matrix representation, you could think of it as a 1 by 1 matrix. That's about as simple of a linear map as you can get, but we'll see the implications of that, and that will allow us to generate a table that show how certain maps generalize to certain numbers. Which numbers are complex, which numbers are complex conjugates, and which numbers are real. Those actually have their counterpart to certain maps. Certain maps look like generalizations of complex conjugates in terms of complex numbers. Certain maps look like real numbers in terms of how they generalize these concepts. That's what we want to put together in the form of a table. Then we will look at a few propositions and corollaries associated with self-adjoint maps. Then we'll introduce this idea of normal operators. That's not to be compared with abnormal operators. And I apologize for those that are listening to this. They didn't get to see an abnormal operator just then. But we might have, and if you were taking copious notes, you missed it also. But it's now a normal operator. What does that mean? That means that the linear map T and its adjoint commute, which means that T dagger is the same as T dagger T in terms of maps. If that's true, then we say that the map is a normal operator, which allows us to conclude or state that a self-adjoint operator does imply a normal operator, but a normal operator does not necessarily imply a self-adjoint operator, and we'll show some examples. You only really need to have one counterexample to show that the implication is not true. Then we will look at this relationship between norms on the output of a linear map and its adjoint. If they take a vector and you map that vector through the map T, or if you map it through the adjoint and the result has the same norm, if those norms are equal, that's another way of establishing that that map is a normal operator. And operators mean we're just starting in a space and we're mapping back into that space when we speak of an operator. If we have normal operators and distinct eigenvalues tell us a fair amount of information, which, hint, hint, know a little bit about that for exam 2. What do distinct eigenvalues provide us with? When do we have linearly independent eigenvectors, etc.? Have that known for, or at least on one of your cheat sheets for exam number 2. If we have a normal operator and distinct eigenvalues, then those are orthogonal eigenvectors, and I doubt we'll get there, but then there's a spectral theorem that we can talk about. This isn't really an analog or a digital class. I was going to say hit rewind. Now let's back up and talk about exam 2 before we move forward into chapter 7. Chapter 7 won't be on exam 2, but the process for exam 2, you now have 3 sheets of notes. That's one more note than you had before, I believe. So it's 2 pages, essentially, 2 more pages. So you don't have to redo your original 2 pages. Didn't you have 2 pages for exam 1? Unless you feel comfortable redoing those. Maybe you want to reorganize those. Maybe it's a good educational opportunity for you to somehow reorganize, but you now have 3. You can bring in a calculator and something to write with, but that's all the peripheral tools you need. And I don't even know if you'll need a calculator, but maybe that's helpful. Okay? No textbooks, no class notes, no cell phones, no computers, no neighbors. I didn't include that, but I hope that's just known, a known fact. Questions on exam number 2. And hopefully that will be available for you to complete on Wednesday. Okay, so now the exam is on me between now and then to create such an exam. Question? I hope everyone caught that that's listening to this audio. I don't know if I can, I'll try to generalize the question. The question was, I think, the exam is, or the material is cumulative. Is the exam going to here's the way I'll rephrase it. Is the exam going to focus or have emphasis on earlier chapter material? And I'm going to say no. But you do have to know the foundational material. We do have to have vector spaces. We do have to have rank. We do have to have dimension. We do have to have range space, null space. All of those concepts you have to have so that we can move into chapter 5 and 6. So the emphasis on the material or the questions will be on chapters 5 and 6, but it may rely on knowledge from chapter 1 through 4. Is that clear? It does build. The class builds on itself. We've now laid the foundation in chapters 1 and 3. Chapter 4 is polynomials. Now we move into 5 and sum of 6. 5 and sum of 6 is what we will focus on for exam number 2 material. Does that ask and answer your question in one? Is that clear? So kind of do your own checking relative to when you're watching the material. You may want to go back and watch on D2L some of the review session for exam 1 dealing with eigenvalues and eigenvectors. That's valid material for this exam too. But some of the material in the review from last fall that is on D2L, it won't be on this exam, meaning the optimization, the Graham-Schmidt orthogonalization, those topics we'll get to for the final and on subsequent homeworks. And between exam 2 and the final, we'll have a project, and we'll talk more about that, I think, after exam 2. So focus on exam 2. Okay, but I have provided some additional resource material for, oh, here. Duh. Here are the topics. Inner products, that's sort of the emphasis piece of the chapter 6, which is inner product spaces. The content is cumulative, which means that we need to have some of the material from earlier chapters, but that's not the focus of exam 2. But I might ask you something about, or I might have you talking about the range or the dimension of a range or something about the null space. You have to know about null spaces if you're finding eigenvectors. Okay? Chapter 2, is that okay? Well, chapter 2. Exam 2, process and material. Chapter 2 will indirectly be on exam 2. Recap, adjoint and adjoint operators. Here's another way of thinking of an adjoint. An adjoint is really defined by this equality of inner products, but sort of look what's happening. The left-hand side, the operator, the linear map, is in the first slot. And it's working on V and W as our vectors. On the right-hand side, you want the inner product to be equivalent to the left-hand side, but now that operator has been slid to the second slot. That's really the definition of an adjoint. The adjoint is whatever needs to happen to basically move that operator to the other slot. That's the concept of this adjoint. If somebody goes, I'm not quite understanding this adjoint, well, it's really, you're just trying to move that operator into the other slot. That's another way of thinking about it. That's the idea of the adjoint. What needs to be done to the linear map or to this inner product to allow that map to be pushed onto the second slot so that you're now performing this linear map on the second slot vector and taking the inner product with the original vector in the first slot. That will make more sense when we move into infinite dimensions, maybe, and we start talking about inner products and adjoints. And now our linear operator might be derivatives, linear operations, second derivative. Now we're dealing with functions. V is now a function instead of a vector. And still, vectors are these items or objects in quotes. They don't have to always be long, skinny things. It can just be a vector of a vector space. So we're playing in this vector space. Now we have an inner product on that vector space, which is why we're now in chapter 6. We're dealing with inner product spaces, which are just vector spaces that possess inner products. And what do inner products give us? They give us a scalar. The output, yes, the output of an inner product is a scalar. And that scalar is useful for, if you've already worked on homework 6, which I hope you've at least looked at since it's due today, the very first question was talking about maybe an angle between vectors. So an inner product allows us to think about distance and angles of vectors. And that we didn't have before until we jumped into or moved into chapter 6. So when somebody starts saying inner product, you might be thinking, oh, norms or lengths and angles relative to two vectors. Yes? So now I'm not sure that I'm completely following your question, but your vector spaces could be complex. But what's the, how do I want to say this? The inner product produces a scalar. And that scalar could be complex. And it has an angle. So you can think of that complex number as a magnitude and an angle. And it really depends on, I think, what you're asking. And I hope I sort of repeated your question. But yes, so what you want to be thinking about is inner product, think lengths and angles. And then see if that helps you or gives you more insight. And all of those depend on the definition of the inner product, don't they? Triangle bracket or angle bracket x comma y, close angle bracket, that's not always the same. You have to be told what's the underlying definition of this inner product. So it depends on the inner product, really, what the results might be. But if somebody says, now, I want the adjoint of that linear operator, you tell them what the inner product, how it's defined, and then they need to figure out, how do I make this equality of the two sides consistent or the same? And that's going to define my adjoint. I'm now moving that operator to the other slot. That's the adjoint. Self-adjoint. Self-adjoint means that the operator, or its matrix representation, is equal to the matrix representation of its adjoint. Let's do some fill in the blanks. If we have a linear operator, t, operating on a two-vector, xy, and the output is ax plus by is the first coordinate, cx plus dy is the second coordinate, what's the matrix representation of that linear operator? A, B, C, D. And you have to kind of know what you were meaning when somebody said A, B, C, D. But now I'm assuming that we are doing it by rows. A, B, C, D. Reading in rows. The first row is A, B. The second row is C, D. If that's the case, and look at what I've put in parentheses, that's the assumption that we're working on. That the basis, that's the plural, but here really if it's an operator, we're working with the same vector space, so we really only have one basis, but you could have a linear map, T, then you would need the input vector space and the output vector space to have orthonormal bases. That's the generalized parenthetical comment. Now, if we know that we're working on orthonormal basis, what do we know about the matrix representation of the adjoint? It's the complex conjugate transpose of the matrix representation of T. If that's the case, then what is B? What's the 1, 1 entry in B? A conjugate. Since if we transpose capital A, the 1, 1 entry stays put, except now we need the transpose complex conjugate, so it's A star. What's the 1, 2 element in capital B? Or maybe the easier one is, what's the 2, 2 entry in capital B? That's the conjugate of what we started with. Since the transpose doesn't do anything to the diagonals, now the off diagonals are interchanged and we have to form their complex conjugate. This is now C star and this is B star. Is that okay? We simply did the we did the transpose, and then we took the complex conjugate of the transpose of capital A to generate capital B, which is the matrix representation of the adjoint. If that's the matrix representation of the adjoint, what's the map of the adjoint applied to XY? The first coordinate is just the first row of capital B applied to XY, isn't it? A star X plus C star Y. My stars aren't very pretty, but they're still twinkling. And then what's the second coordinate? B star X plus D star Y. And you need to be very comfortable with this movement of maps to matrices for the exam. So we're kind of studying for the exam even though we're in chapter 7, right? Where was I going with this? Oh, we were trying to talk about self-adjoint operators, which means that we need these maps, their matrix representations, or these maps to be equal. If we now say, oh, I have a self-adjoint operator, that's true, or if and only if these operators, the operator and its adjoint, are the same. And if we apply that now to these matrix representations of capital A and capital B, then we can see a correlation between these entries, these scalars, in our operators. Meaning, if the above linear map T is in fact self-adjoint, then we know that A is equal to A star, B is equal to C star, C is B star, and D is D star. We have A equal to A star, and D is equal to D star, and that says that if we have a scalar and it's equal to its complex conjugate, then the imaginary part is not there, or we now have real values on our diagonal, real scalars on our diagonal of these self-adjoint maps. The diagonal elements are real. We also, by comparing elements in those matrices, we found that the off-diagonal elements are complex conjugates of each other. And we can think about that in general. And I cheated. I wrote this down before class, and I was hoping I allowed myself enough space. And I did. But this now just says that you can fill in the diagonal of this matrix representation of T. The diagonal is simply all real. And the off diagonal, so now just populate the off diagonals with the standard subscripted scalars, A12, A13, all the way up to A1n. All of those above the diagonal we can just call the normal A's, and then simply take the transpose effectively, take the row and make that the column, and conjugate all of those, and that now leaves us with this structure for a linear maps matrix representation with all the diagonal entries being real. That's the general form of a self-adjoint operator. And that's what we just sort of showed for this 2x2 case. And this form is true this form for the matrix representation of this linear map T is true for any basis. And in fact, if you have a very special map that ends up having a matrix representation that's diagonal, a diagonal matrix will have that structure under what condition? As long as those diagonal entries, those scalars on the diagonal, are real. So a diagonal matrix has this structure if the diagonal elements are real. Let's now look at an example of a self-adjoint map, and it's going to be a simple example. Let's examine a simple map and see how the concepts from this simple map might generalize. Here, this simple example is showing that the matrix representation of an adjoint is the complex conjugate transpose of the original map T. So if you get lost in this simple example, just go back to this blue sentence. It's just showing that in the matrix representation of this simple map, it's just saying that we're dealing with the adjoint being the complex conjugate transpose. All right. Another way of thinking of that is that the matrix representation of the adjoint operator is and it really doesn't matter which one you do first, but the star is the conjugate and the T is the transpose. We take the matrix representation of the original map T, transpose it, and conjugate all of the entries. That's the concept. And that assumes what? That we're dealing with all of these on orthonormal basis. So that assumption is what is underlying this whole process. Here's our example. Suppose the linear map T, or the linear operator, takes the complex field back into itself. From C to shining C. No, just from C to C. Sorry, I just couldn't. So now we're going from complex to complex. We can now illustrate that by saying we have T of X is, let's say, A of X, where A is in our field of numbers, which we are saying is complex, and X, our vector, is also a member of the complex numbers, or an element of the complex numbers. You give me a vector X, which is coming from the complex numbers, and the linear operator that I'm defining is just going to scale that by another complex number A. That's the mapping, the linear map that I'm referring to or using. To emphasize what we have, A is really C in a 1 by 1. It's a scalar. And complex scalar, or a complex one-by-one matrix. And for that reason, then, the matrix representation and we're assuming the standard basis, which the standard basis is just 1. But now the matrix representation of T is A. And again, if we wanted to really keep track of things, that A is a 1-by-1 matrix, if we wanted to generalize. Now let's apply this or use this linear map or operator to define an adjoint. Let's apply the definition of the adjoint. To see what the matrix representation of the adjoint of this 1 by 1 matrix looks like. And the definition of the adjoint gives us what? Answers? You've already written down your answer, I hope, while I changed out my batteries. Batteries in my microphone, not in me. I wish I could replace my batteries. They're not as easy to recharge. We have Tx V equaling, and now the adjoint that we want simply slides that operator into the second slot. So that this is now supposed to equal x, the adjoint applied to V. Let's now use, so there's our definition of the adjoint. Let's use the Euclidean inner product as our inner product. We have to pick one. Let's use the Euclidean inner product, which now says that I have t of x, that's the vector of the linear operator applied to x, times each coordinate in V, complex conjugate. So each vector in the output, which in this case it's just one coordinate, but if we had this in multiple dimensions, then we would have each coordinate matched up with the coordinate in V, and V has to be conjugated. Here we simply take V star, since it's a scalar. And that now, based on the right-hand side, needs to be x times the conjugate of the output of the second slot, and that's just T dagger V complex conjugate. That's applying the Euclidean inner product. So I'm going to do this in a few steps, but what is T of x equal to? We agreed that that was our linear operator, and we said that was AX. So we have AX times V star. And that's now equal to the right-hand side, and we didn't say what T dagger V was. Let's just agree that that's some B times V. And B we've yet to determine. So let's now say that that's X times some B V that we are conjugating. This is yet to be determined. This B is an unknown scalar. That's what T dagger V produces, is BV. Is that okay? And we need to find what B is. But this now says that we have X, B conjugate, V conjugate, but B is a scalar, so we can slide that through. All of these three things are scalars, so it really doesn't matter which order we're doing it in, but we now have B star X V star. And now we can compare that with what we had on the left. We had an XV star on the far left. We have an XV star on the far right. If those are equal, we wanted the inner products to be the same. And we can make the adjoint have that property if we allow B star, or its conjugate of B, to equal A. And then we have the adjoint. We know what B is. Therefore, B star is equal to A, or B, which is the scalar associated with the adjoint, B is now equal to the complex conjugate of A. And that now allows us to say that T dagger V is now BV, which we just derived to be the complex conjugate of A, V. Or if we wanted the matrix representation of T dagger, that's now the complex conjugate of A. Or the adjoint map, or the adjoint of a map, is the generalization of the complex conjugate of a complex number. And we showed that with a simple map of going from C to C. What if we specialized that map to be self-adjoint? So now we've learned that taking a scalar and finding its complex conjugate can be generalized into this map. If we have a linear map, then the generalization of that is that's like just taking the complex conjugate of a complex number, finding the adjoint of a linear map. What about a self-adjoint operator? If it's self-adjoint, then the maps are the same. And if the maps are the same, we learned that the matrix representation of those two maps, T had A, T dagger was its complex conjugate, and the only way for A to equal its complex conjugate is for A to be a real number. That now allows us to think in terms of sort of a table. If we looked at a certain number, what or how can we generalize that, or generalizes to a certain map, meaning if we now had a complex number, let's say Z is A plus JB, a complex number, that's just our linear map. We said A was a complex, oh man, I'm overusing A, aren't I? Is it clear from the context what I'm meaning? So in my early, wow, maybe I should have done something different. So let me call this. So this is what I called A before. Can that be any more confusing? So I'm now wanting to use, I didn't think of that before when I was writing up. It all seemed so easy or so clear, but It's only because I was creating it that it was clear. Z is now what we were saying A was before. So now I've subscripted these A's. It's A1 plus JB1. That's not the same A as before. Is that okay? So before we had a linear map A. Now just think that linear map is Z. But a lot of times we've used Z for coordinates of a vector. But now I'm switching to using Z as a complex number, since Z is typically a complex number by itself without a subscript. Oh man. Here I'm just wanting it to be thought of as sort of the scalar version of a linear map, T. And if we look at something a little bit more complicated than just a scalar mapping, then T is sort of this generalization of a complex number. What if we now say we have the complex conjugate of that, so that we now have A sub 1 minus JB sub 1 now we've seen that that's can be generalized to the adjoint map. Meaning, if you start getting all hung up on these maps and what they mean, just go back to this table and say, well, that's not anything more than the complex conjugate in the simplest case, if somebody starts talking about an adjoint. Or think of this adjoint as what needs to happen in the second slot to essentially make the original map be slid from the first slot to the second slot. And that's what's going to define my adjoint. Finally, if Z is equal to A sub 1, where Z is now just real, a real number, then T is a self-adjoint map. Now we've defined some of these concepts. A linear map we've had, or a linear operator we've had. Now we created inner products. We can now use those inner products to slide a map between the two slots, and in so doing we've actually created an adjoint, a concept of an adjoint. And we can now think about these maps being generalizations of complex numbers. Now that we have that, let's look at some propositions. Proposition 1 in chapter 7, proposition 7.1 says that every eigenvalue of a self-adjoint operator is in fact real. Let's see if we can convince ourselves of that. We're saying that we have a linear operator on some vector space capital V, and that could be a complex vector space. But now we are saying that that linear operator is equal to its adjoint, if it's self-adjoint. If this is true, what's the eigenvalue-eigenvector equation that we can use? Again, we're reviewing for exam 2, aren't we? Okay. Now somebody says, I want to watch TV. You say, oh, that's great, lambda V. So TV is lambda V. And we're saying that lambda and V are the eigenvalue and eigenvector associated with t, and t could have several of these. But now let's just keep them in general terms. Let's now look at what happens when we examine the norm squared of v scaled by the eigenvalue lambda. And again, the norm of v depends on the inner product that we're using for that norm. But it's not going to be, we're not going to have to clarify that. This will be independent of the inner product that we select. But what's the norm squared of a vector? The inner product of v with itself. This is now lambda v, or bracket v comma v, close the angle bracket. But we can push that scalar into the first slot without much effort because of the homogeneity of the first slot. This is now angle bracket lambda v, inner product with v. What we've done is we've just used the definition of the norm and the homogeneity of the first slot of the inner product. And that you need to be able to do for exam 2, right? Now that we have lambda v, we just said that that's the same or equivalent to the linear operator t applied to that vector v by the eigenvalue-eigenvector relationship. And we can now replace that first slot, lambda v, with tv. So that we now have this is equal to tv v. That's just the eigenvector equation, or the eigenvalue-eigenvector equation. But now we know the definition of the adjoint. We can move that operator to the second slot by the definition of the adjoint. This is now equal to v t dagger v. But we said that t was self-adjoint, didn't we? So now we know t dagger and t are equivalent, or are the same. So let's replace t dagger with t in the second slot. This is now v t v, and that's because we had t being self-adjoint in our proposition. That was a given. But we know TV is lambda v, don't we? That again is our eigenvalue-eigenvector equation. And we know this concept of what happens when we have a scalar in the second slot if we want to get it outside of the inner product. It's the conjugate, isn't it? So we now have the scalar lambda slid outside the inner product, but we have to take its complex conjugate to make that true. So now we have lambda star v comma v, and that's the conjugate homogeneity property of the second slot of our inner product. But now the inner product of v with itself is just the norm of v squared. So that we now have lambda star norm of v squared. I can't fit it on one screen, but what do I have? I have the far left expression, lambda times some number, the norm of something squared, that's just a number, equal to lambda conjugated times the same number. the same number we're assuming is non-zero, we can divide that out, and now we have lambda is equal to its conjugate. And the only way that can happen is if that scalar is real. So now we've shown that every eigenvalue, we didn't specialize lambda and v when we started, we just say lambda and v, if they're eigenvalues and eigenvectors of this operator t, then it has to satisfy this eigenvalue-eigenvector equation. If that operator is self-adjoint, then every eigenvalue is real. We've shown that lambda v squared is equal to lambda star norm of v squared, which allows us to say that lambda is equal to its complex conjugate, or that all eigenvalues are real. So now, if you have a self-adjoint operator, it has some pretty specific properties or characteristics. If you try to find the eigenvalues and you come up with those being complex, you go, was this operator self-adjoint or not? Maybe I had an algebra mistake. Something's not consistent. Let's look at some property or propositions and corollaries for these self-adjoint operators. Several propositions and corollaries from the textbook. And you can look at the text for the justification of these propositions and corollaries. Proposition 2 in Chapter 7, if V is a CIPS, complex inner product space, if V is complex vector space that possesses an inner product, so it's now a complex inner product space, and T is an operator on that space, such that it has the following property. The inner product of TV with V is equal to 0 for every vector in the complex inner product space V, then we can actually conclude that that linear map is the zero map. And that's true for any complex inner product space and a linear map T on that complex inner product space. If we look at the inner product of that map with the same vector, and it equals 0 for all V, then we can say that that was actually the zero map. A corollary. Corollary 7.3, if V is a complex inner product space, and again T is a linear map, then this linear map T is in fact self-adjoint if and only if, when you compute the inner product of TV with V and you obtain a real scalar for all vectors V in this complex inner product space V. then you can say that T is self-adjoint. Or if T is self-adjoint, then you can always know that TV comma V, the inner product of that is supposed to be a real scalar. Proposition 4 in Chapter 7. If T is a self-adjoint operator on V such that TV comma V is equal to 0, then T is equal to 0. So this actually extends, so this proposition extends proposition 7.2 to real inner product spaces. We didn't say anything about V here in proposition 7.4. We didn't qualify it here. In 7.2, we said that V was a complex inner product space. And remember, we can do sometimes more with complex vector spaces than we can with real vector spaces in terms of eigenvalues being existing or not. We can have rotations in a real vector space that do not possess eigenvalues as far as maps are concerned. Here, in proposition 7.2, we're saying that V was a complex inner product space. In 7.4, we didn't say anything about V. So now 7.4 just says you have a inner product space, capital V, such that TV is V, inner product with V is 0, then T is equal to 0. But we've specialized this map, T, to be self-adjoint. That's the restriction here. So proposition 7.4 extends proposition 7.2 to real inner product spaces, but it adds the requirement of T being a self-adjoint operator. Yes. So now the question was, since the reals are, in a sense, sort of a smaller space, maybe, than the complex space, why doesn't 7.2 apply to reals? And it's sort of the fact that the reals are smaller than the complex. It's being too restrictive, and so that doesn't necessarily allow you to produce this result when V is, let's say, little v's, these vectors are restricted to being real. Okay, so that's not shown here, but you might look at some examples that might actually illustrate that there might be a rotation or something like a rotation whose inner product with the vector V itself produces 0, so maybe there's some orthogonality there, but yet the map T is not identically 0. So now playing on the real vector space is more restrictive than playing on the more encompassing complex vector space. So the fact that you're sort of restricting to the reals imposes more, and if that's the case, then you basically need something more restrictive on this map. Your T needs to be self-adjoint. And we sort of know what self-adjoint means in terms of its properties. Okay? Let's now look at a new concept, which is normal operators. We now have linear maps or linear operators. We have their adjoint. Now let's talk about a normal operator, and a normal operator on an inner product space is one where T, the linear map, commutes with its adjoint. That is, or i.e., T dagger is equal to T dagger T. A consequence of this definition is that all self-adjoint operators are normal operators, since if it's self-adjoint, T equals T dagger, and if you now have T dagger, well, you could say that that's T, since T dagger is equal to T, and now we can say, well, the first T is equal to T dagger. That's true. So that now T dagger is equal to T dagger T. That's implied when you have a self-adjoint operator. However, normal operators do not have to be self-adjoint. Normal operators can include I just felt like hyphenating, non-self-adjoint operators. Let's look at an example that's in the textbook, just to convince ourselves that that's true. Axler gives example of T or its matrix representation, the matrix representation of a linear map, T. Suppose that the matrix representation of a linear map T is 2, -3, 3, 2. And I may call that capital A. Is that self-adjoint? Self-adjoint means the matrices need to be, their transposes at least have to be the same, right? If they're real, because the complex conjugate doesn't do anything. So we need the transposes to be the same, and that's A is not equal to its transpose. This is now not self-adjoint. What's the linear map T associated with that matrix representation? The first coordinate is 2x minus 3y. The second coordinate, 3x plus 2y. What's the matrix representation of T dagger? We can go back to the matrix representation of T and just take its complex conjugate transpose. That's the matrix representation of T dagger, so that now we have 2, 3, minus 3, 2, and I'm going to call that B. Is that okay? Then we can say that the linear map of the adjoint, T dagger, applied to xy is now 2x plus 3y in the first coordinate and minus 3x plus 2y in the second coordinate. And what's AB? We've already seen that A is not T is not self-adjoint. But we're going to show that T dagger is equal to T dagger T. So we need to show that AB as a matrix will produce the same matrix as BA, because then we could find their maps. AB is now 2, minus 3, 3, 2. B is 2, 3, minus 3, 2. You can show yourself at home tonight that that ends up being diagonal 13, 0, 0, 13 if it's not clear right now. BA is now 2, 3, minus 3, 2, and 2 minus 3, 3, 2. Again, that ends up being the same diagonal matrix with 13 on the diagonal. A, which was equal to this 2 minus 3, 3, 2, is not self-adjoint, but 2, 3, minus 3, 2, or maybe I should just repeat it. Let me repeat it. But 2 minus 3, 3, 2 is a normal operator, or the matrix associated with a normal operator. Is that okay? Let's look at one more proposition related to normal operators before we have to finish. An operator, T, on a vector space V is normal, and we now know what normal means. It commutes with its adjoint, the operator, if and only if the norm of TV is equal to the norm of T dagger V. So if you can now show that the norm of TV is equal to the norm of T dagger V, then you can now say, oh, that linear operator was normal because of this proposition. I'll let you work through the proof before we meet again for lecture on Monday, but make sure and show up Wednesday for exam number 2.